In this next video, we will look at the building blocks of convolutional neural networks as well as the key implementational differences between CNNs and fully connected networks. When transitioning from thinking about MLPs to CNNs, the first thing you need to do is stop thinking about the units of networks as neurons and start thinking about networks learning hierarchical sets of filter kernels, which can be used to intelligently compress images into compact representations where they can be compared, segmented, or classified. This is because, in contrast to fully connected networks, CNNs no longer connect all points in an input image to every coefficient in a weights matrix. Rather, each neuron in a convolutional network sees only a very small part of each image referred to as its receptive field. This local connectivity means that each neuron must only learn a weights matrix of dimensions f by f by d. Further, due to enforced parameter sharing, the same weights kernels must be learnt by all neurons. This means all points in the image element-wise multiply with the same local weights tensor, such that the whole thing reduces to a convolutional operation. And typically, more than one kernel is learnt by each layer, where the number of kernels learnt will decide the dimensions of the activation tensor output from that layer. Specifically, if we use padding to enforce same convolutions of an input image of dimensions 32 by 32 by 3, and we train 12 filters, our output dimension for that layer will have shape 32 by 32 by 12. For example, let's simulate the operation for this square RGB or red, green, blue image of a flower with equal height and width h and depth d0 equal to 3 for the red, green, and blue colour channels. Let's say that we learnt I filters of shape f by d0. Always the filters must have depth equal to the depth of the incoming image or activation layer. When convolved with padding p and stride s, this will return an output image of shape h1 using the formula learnt in the previous lecture. The output of this operation is likely to be something like that from an edge detector, as early layers learn simple local filters. The user will define how many filters to be learnt at each layer. So let's say you choose 64, indicated by this variable d1. Then the final output of each convolutional layer will also have depth d1, 2 by 2 activational images, each representing the output of the convolutional operation from one of the filters from the previous layer. The forward operation is therefore learnt quite similarly to fully connected networks. However, as previously stated, rather than allowing each neuron to connect to all features in the previous layer, it's only got local connectivity, specifically the connectivity corresponding to the dimensions of the input kernel, for example 3 by 3 by 3. Thus, the output of the convolution at location 0, 0, 0 corresponds to the convolution of the kernel W0 as shown here with the top left-hand corner of the image, and the output of the convolution at location 0, 1, 0 then corresponds to the convolution of the same kernel with the exact same weights, W0, shifted along by 1, and so on, convolving in the exact same way as previously demonstrated, but this time using notation similar to that which we saw for the first lecture on fully connected MLP networks. This whole process then repeats for the second filter W1 and indeed all subsequent filters, where the results of the convolution for each different filter populate each of the depth channels of the output. So here the results for kernel 1 fill the first index of the third axis of Z, whereas the first kernel filled the 0th index. And using vectorization, this operation can be calculated very quickly by first reshaping each local image block into a vector. Here, of row length 9, since 3 times 3 is 9, and we're considering a 3 by 3 kernel. And then these patches can be stacked together to form a matrix. And if the same operation is essentially performed on the weights tensors in order to convert these into a 2D matrix where the columns correspond to the number of weights per kernel, so F times F or 9 in the previous example, and the rows equal the total number of kernels DL, then convolution may be simply performed through matrix multiplication. Not forgetting thereafter that, as with MLPs, CNNs must follow convolutions with element-wise activation operations in order to ensure that the networks can learn nonlinear functions. Then, considering backpropagation, convolutional layers have a nice way of backpropagating their errors by again making use of the convolutional operation. So here, this is the forward operation with the asterisk highlighting the convolution. As we've already seen, this is an element-wise multiplication and sum of overlapping elements. So Z11 equals W11 times X11 plus W12 times X12 plus W21 times X21 plus W22 times X23, and the equivalent for the shifted position here. Then, if we subsequently look at the partial derivatives of the loss estimated with respect to the parameters, we note that these take the following form according to the rule of total derivatives. And since the partials of Z with respect to W, for example, Z11 with respect to W11 here, are elements of X, this means that this also reduces to a convolution of the following form, where the elements of X are now convolved with the partial derivatives of L with respect to Z. So backpropagation again reduces to matrix multiplication operations as before. So that's the high-level differences which occur during optimization, but what are the key building blocks that we should be aware of when creating our CNN network classes? Let's start by considering downsampling. Networks need to be able to downsample in order to increase their receptive field, reduce parameters, and increase representational power of their features. We'll first look at how this can be done through pooling. There are several types of pooling operation, but the basic idea is to downsample by aggregating blocks of elements into one through min, max, or averaging operations. For example, here we're looking at a max pool. If we use a pooling filter of shape 2 by 2 with a stride of 2, we can see this reduces the shape of the image by a factor of 2 by taking forward only the maximum elements of each filter block. So specifically taking the first 2 by 2 block shown in yellow, the maximum value here is 9, and so this becomes the first element of the top left of the downsampled block. Then for the green block, the max value is 7, so that's propagated here. For blue, it's 3, and for red, it's 9. Backpropagation through max pooling is then performed as follows, where if we use the following notation to indicate the forward operation, such that for some block corresponding to the pooling kernel, let's say for argument's sake the yellow block, the output can be written as a weighted sum over all elements of the block, where the weights are only non-zero for the largest element, as indicated by the element returned from the max operation here. We already know from previously looking at the gradient of the element-wise ReLU operation, which is also a max, that the partial derivative of the loss with respect to some parameter is just 1 for elements for which max is true and 0 elsewhere. Therefore, tracking backwards as we did with the ReLU in the fully connected network, the gradient of the loss with respect to the incoming activation will either just be the gradient coming in from the next operation in the network, in other words the pooling operation, propagated to the location of the max element from the forward operation, or if it wasn't the max element, then the gradient is just going to be 0. Clearly, to implement this, the network must keep track of these masks as they propagate forward. More commonly nowadays, however, downsampling is performed through strided convolutions, for example, as follows. This is because it's felt that this increases the model's expressivity, as it can be seen as learning the pooling operation, The slight downside being that the network then needs to learn more parameters, which might be a problem if the dataset is small. Another trick that you might see is the use of one-by-one convolutional blocks. By one, what I mean is use of a kernel that looks like this orange block. So it has 1 pixel in height and width, but as always with CNNs, the depth of this kernel has to be equal to the depth of the incoming block. The idea is that one-by-one kernels allow for data to be compressed or upsampled through learning a change only to the number of channels, so just compressing across channels, since when convolving an incoming blue block of shape h by w by d with this orange one-by-one filter, the output will be a 2D block of shape h by w by 1. And so if we learn n of these, then the dimension of the output will be h by w by n. So what these are typically used for is to first reduce the channel dimensions. In other words, n would need to be less than d, so as to allow some computationally heavy operation to be performed that requires lots of parameters proportionately, after which another 1 by n convolution can be applied with d filters, which will then rescale the output back up to the original dimensions. Use of this type of operation can improve the efficiency of networks by reducing the number of parameters that need to be learnt, and in this way it can help to reduce overfitting. Next, let's look at the batch normalisation or batch norm operation, which was introduced to stabilise training. As we will see in the session on optimizers, deep networks are typically trained with variants of stochastic gradient descent, which, as you might suspect from its name, samples datasets as batches, a necessity for very large datasets, rather than estimating the loss across all examples. And as a result of this, the technique is stepping in the direction of gradients estimated for these much smaller batches, which, because these can vary quite a bit depending on the composition, can be quite noisy. Batch norm smooths the loss and as a result supports taking larger steps in the direction of the gradient. As a result, this speeds up training. The operation itself is as follows. So first, the mean and variance must be estimated across the batch for each variable input to the layer, shown here by the variable x. Then, normalisation is performed by subtracting the mean and dividing through by the standard deviation, where the epsilon prevents division by 0. The goal is to ensure updates are of comparable size independent of what data goes in, this being known as covariate shift. Finally, multiplicative and additive bias terms are learnt. It is thought these learn to intelligently rescale and recenter the network's activations so as to shift the output prediction into the correct learning regime, and in this way speed up training. For more details and an intuitive explanation of how this helps, please reference this fairly recent NeurIPS paper. Finally, and importantly, note that the gamma and the beta here are trainable parameters, one learnt for each index of the input tensor, which is why batch norm operations must be defined in the constructor of the PyTorch network class. Next, and almost last, we'll look at dropout. So dropout is a technique which has historically supported network regularization so as to improve generalization at test time. It does this by randomly dropping activations during training, where each line in this diagram shows multiplication of an activation with a weight. So during dropout, some of these are just zeroed for that specific training batch. In other words, the output of some neurons is just dropped from the network temporarily. No signal can flow through these locations, a bit like applying a hand-engineered masking operation on the output of each layer. The reason why this is useful is it stops individual network components from memorizing the inputs, something which would lead to overfitting. There is a trade-off, however, as dropping too many weights will prevent the network from learning well enough, causing underfitting. Note, when implemented for regularization, dropout is performed only at train time. At test time, all activations must be retained to take advantage of this distributed learning and make a full prediction. The problem is that during dropout, the remaining nodes are having to work extra hard to make the prediction, so activations will be scaled up relative to what they would be if no dropout was applied. This means that at test time, when all nodes are present, it becomes necessary to scale the outputs back down, or, as PyTorch instead implements, apply correctional or upscaling during training. However, this can actually create a problem if you implement batch norm and dropout together in one network, because one is applying a test time correction to its rescaling and the other one isn't. As a result, dropout for regularization has fallen out of favour, although some modern networks still successfully place a dropout layer before the last batch norm layer, because this does not shift variance. And as we will see next week, the designers of the wide ResNet network managed to get dropout to work by placing it after the activation layer instead of before. So there is some suggestion that the way in which layers are ordered is important. Accordingly, when it comes down to it, what order should you be organising your layers? Well, traditionally, this is the order suggested. For example, this is the order that was suggested in the original batch norm paper. Batch norm applied before the activation. Technically, the order of a max pool and a ReLU doesn't matter since they're both element-wise operations and so commute, though the following is the order where it's most commonly seen. If dropout is being considered, then the recommendation is that it goes at the end. Alternatively, you may choose to swap out the pooling layer for a strided convolution, in which case this structure might be seen. But having said all of that, if you look through this Stack Overflow discussion, you will see reference to how some quite prominent members of the field advocate for putting the batch norm after the ReLU. So it's possibly worth experimenting with and/or doing some reading around the literature or discussion boards for yourself. Finally, a very quick note, as this will get discussed in more detail in the uncertainty lecture in week 10, even if dropout has fallen slightly out of favour as a network regularisation tool, it remains a useful tool for instead measuring uncertainty at test time. Seeing as, if we drop out different activations at test time, we're going to get a different prediction each time. So we can do it many times and see which regions of our network are most susceptible to change, and these will be the ones we're least sure about. For example, the edges of this prediction of fetal head circumference as measured from ultrasound in a paper by Samuel Budd, a current CDT student. And so the final component we need to consider is a fully connected or linear layer, where importantly these expect flattened or vectorized inputs and are used to reduce the number of parameters right down to the required number of predictions. For example, 1 if we're targeting binary classification or single output regression, and K for multi-output predictions. The problem with using fully connected layers is that they require hard coding of the number of expected inputs, since by design they need one neuron for every feature incoming from the previous layer. This amounts to hard coding the required size of the data input to the whole network. Therefore, fully convolutional networks were invented instead. These get around this requirement by replacing the fully connected layers with convolutional layers, which do the same thing. So, for example, if the penultimate convolutional layer, in other words, the final convolutional layer before what would have been the fully connected layer, has shape 7 by 7 by 256, a fully connected layer with 4096 neurons can be replaced by a convolutional layer with 4096 kernels of shape 7 by 7 by 256, because convolution of each one of these kernels with the whole image will just return one single value. So in this way, you're no longer constrained to have a particular input size, which turns out to have very important implications for semantic segmentation, as we will see next week. So in summary, the goal of CNNs is to learn bespoke convolutional filters for effective image compression and representation learning. The building blocks of convolutional networks are convolutional layers, downsampling operations, either pooling or striding, and activations. Secondarily, you have the option of also including batch normalisation and dropout layers to regularise and improve training and/or generalisation, where batch norm is used much more often nowadays than dropout. Forward and back propagation in CNNs is implemented similarly to fully connected layers, except for that there is no longer full connectivity between layers. Local regions of images are connected to local weights kernels. Each local region is then forced to learn the same weights as its neighbours, otherwise known as parameter sharing, which therefore means that the weights learn convolutional filters. Finally, a couple of useful tricks to remember. One-by-one convolutions can be used to reduce the number of filters or kernels and thus network parameters, which can allow more efficient and generalizable computation. And convolutional layers can be used to replace fully connected layers to make networks invariant to input dimensions. So that's it for this introduction to CNNs. Please now complete the Keats quiz before quickly reviewing the last video on the PyTorch implementations.